Right, so this video is going to run through atomic structure. It's going to go through the general sort of bits of the atom, and then it's going to lead into electron configuration. It's not going to have any mass spectrometry in or anything like that. It's purely just going to be bits about the atom, general points, bit about relative charges, masses, etc., relative atomic mass. No calculations of that, and then it's going to be predominantly electron configuration based. Right. So this is an atom of sodium. Okay, and what we've got here, it's an atom, and it's a diagram which it's probably more akin to GCSE, where you've got this classic 2-8-1 in the case of sodium here. So this 2-8-1 electron configuration here. Each one of these crosses is of course an electron, and in this case we have 11 electrons present. So 11 electrons within this atom here. Now, a few things about that. So, a few things about the rest of this diagram, really. Leading on to a later point, really. Each ring is equal to an energy level. And in this case, you can see that we have 3 energy levels. So, 3 field energy levels. The first one here, second one here, and third one up here. And that's the important thing, really, is the order in which these are. The first energy level is the one closest to the nucleus, the second is the next one up, and the third one is the next one again. Right, so what else is this diagram showing me? So I've got electrons, I've got electron shells, or energy levels as they can be called. I'll actually put this here. Shells is another way to word that. Other things I've got, well, I've got this thing in the middle here. I've got a nucleus. Now, a nucleus is fairly important. It's the centre of the atom. It's this incredibly dense, in relativistic terms, to the rest of the atom, where almost all the mass of the atom lies, and it's a very central point. And then in between the electrons and here, we just have essentially empty space, which is a strange idea, but there you go. Nucleus. This is made of protons and neutrons. And what we find here is that protons and neutrons, well, each one of these, I'm going to say quite a lot in this short space of time because I feel it's GCSE and therefore there's not really any need to sort of dwell on it a huge amount. Protons and neutrons, they give us the mass number, or better terms, the relative atomic mass of an element. And you'll see that in the periodic table. So in the case of sodium, and I'll try and remember what it is now. I think it's Na. I think it's 23.1. I think it's 23.1 and 11. That's what its little square on the periodic table would look like. And in this case, the relative atomic mass is this guy here. Okay, this top, the bigger of the two numbers, which leaves us a bottom number. Now, this bottom number is the atomic number, and in atoms, not ions, atoms. The atomic number is equal to proton number, and that is equal to the electron number. And that's why I'm saying atoms here. We're dealing with ions, we're changing the numbers. It doesn't work. Proton numbers and electron numbers is the atomic number. So, a couple of bits. Protons and neutrons, well, they equate to this mass number. The reason being that each one of these has a relative mass of 1. So relative masses of 1. Electron, we can say, has a relative mass of approximately 0. It's about 1 over 1,187 or something, but it's, again, relative terms, it's 0. Charge-wise, why do the number of protons equal the number of electrons? Well, charge-wise, overall atoms have 0 charge. So atoms are neutral, a better way to say that. And that's because protons have a charge of +1, electrons have a charge of -1, and therefore when they're equal, we have a 0 charge. The other thing being that neutrons have a relative charge of 0, therefore they have no effect. So that's quite a quick sort of recap, I guess, in some ways of sort of this idea of the atom, and particularly then these electron configurations. And that's what I now want to spend a bit more time on, is these electron configurations and how we can develop that in A level, and why this is a simplistic model. It's one that works, the Bohr model. It certainly works in many ways, and it isn't, strictly speaking, wrong. But to the level you do it at GCSE, there are a couple of not lies or fibs as such, but there are a couple of simplifications, and that's often why when you're at GCSE you have to learn up to calcium. You don't go into the transition metals, because at that point things get a bit weird, which hopefully by the end of this video you'll have an understanding of, and you'll know why they get weird, and actually why the delightful people at AQA chose to stop it at calcium rather than move into I've completely forgotten the next, scandium I think is the next one, and then titanium. So they stopped calcium for a reason. So, electron configurations. Now, as we've already seen here, and this is true that electrons exist in energy shells. So we have energy shells, or we'll call them energy levels, or actually we'll go energy levels slash shells, best of both worlds. And they can be anything from, they're often given, that's given the symbol N. You're not really need to know that. Starting on the inside, we can go 1, 2, 3, 4, and that's probably about the extent that you're going to get to in the AS. You're not going to get any further than that. So we've got 4 energy levels, or a bigger number, but 4 is just what we really need to look at. I warn you at this next point, you're probably not going to have a clue what's happening, but the best way, whenever I teach this, I find that people just kind of get really confused, but hopefully it's sort of the penny drops towards the end. So there's a lot of weird information, and it's difficult to know what order to do things, but hopefully this will make sense. So electrons are found in energy levels. Now each one of those energy levels is split into what's called subshells, and they are given the letters S, P, D, and F. That's a fairly strange idea, but even more strange than that, each one of these is split into orbitals. Oh, nice colour. And these orbitals work as follows. The S is 1 orbital, the P has 3 orbitals, the D has 5 orbitals, and the F has 7 orbitals, of which you don't really need to worry about. F is an annoying one, really. We can just kind of exclude that. For the sake of the AS, S, P and D are what you guys are going to be looking at. And then, slightly easier one here, each orbital holds 2 electrons. Note that I mean each orbital, not each subshell. So actually what it means is that S equals 2 electrons because it's got 1 orbital, P equals 6 electrons because it's got 3 orbitals, and D equals 10 electrons because it has 5 orbitals. Now at this point you are not going to have a clue, I would guess, what's happening, and the whole thing just seems very strange, and you have no idea where these subshells have come from, all these orbitals and all the rest. Now this whole thing can get quite difficult when you start thinking about electrons and all the rest, and so I don't want to go into a huge sort of amount of detail as such. More the orbitals really are, when we think of electrons, the idea of this Bohr model implies that electrons are very static. They're just sat, or they're orbiting is another idea. Electrons orbit the nucleus, which isn't really true. The electrons can exist in, really, as far as I'm aware, sort of anywhere they really want to. And what these orbitals do is, the orbitals are really the place where you're most probable. I think there's something like a 95% chance that the electron will exist within this area of orbital. So it's an area of the atom, really, the orbital is, and that it's the area where the electron is most likely to appear. Now you don't need to know that in an exam. In terms of an exam, what we have to be able to do is use this to write an electron configuration for an atom or for an ion. But you don't have to worry about the reasoning behind it, but that's really kind of it. The orbitals are where the electrons are most likely to be found. Now if you want to look this up, ChemGuide's got quite a good explanation on orbitals and all the rest. I don't want to go into details for it because I'm looking to sort of cover this for the masses as opposed to those people who really want to go into sort of quantum land and do all various bits. I don't want to be there, to be quite honest. I'm quite happy here, and so I'm going to leave this at this, and I'm going to add one more thing to this, and then I'm going to actually look at sort of what we're doing. In fact, I'll put that next bit down here, and then I'll give you some examples of stuff. Final thing I want to add on, or to point to this, is the order of which things work. So the first energy level has an S subshell, and that's it. Second energy level has an S subshell, and it has a P. The third one, perhaps see where this is going to go now, has an S, it has a P, and it has a D. The fourth one has an S, has a P, has a D, and it has an F, although we're going to, for the sake of this, we're going to kind of ignore the fact that the F exists. It's just needless confusion for now. So, the reason I've drawn this diagram this particular way is because it's very important, because it tells us how these things fill. And I will give you some examples, so this should hopefully make sense. But as I said, at the minute it's perhaps just very confusing, but bear with me. The electrons fill these things. Starting here, we go down, across there, across there, across there, and down. Okay, and 4p is about as far as actually as you're going to get. I think the furthest you have to go is krypton, which is as far as you're going to go. So you actually don't even need to worry about the 4d, in all honesty, just this. Key thing here is, though, this goes as you'd imagine, 1s, 2s, 2p, 3s, 3p, it then goes 4s before 3d, and then it goes 4p. And if you look at a periodic table, this is because actually what we find is that we separate the periodic table into particular areas. So this here this is the D block. This up here this is the S block, and finally this one over here P block. So S, P and D. And actually if you start thinking about, well, what's going to happen when I'm actually going these electrons? Well, we start up here. This is going to be our 1s. It's going to be our 1s, 2s. Sorry. This is going to be one of the 1s's, and this is going to be the second 1s. We're then into this section here. We're adding the 2s, and then we're into the 2p, 3s, 3p. Well, now we're into the 4s, but then it drops into a 3d, which is a new one, followed by the 4p. So if we think about it in this section, in this way, so we go 3s, 3p, 4s, 3d, 4p, and then it would then go 5s, 4d, 5p, and actually you end up with the F, I think, comes in about here. It might be one lower, I forget where that exactly squeezes in. But you are expected to know this is the S block, this is the D block, and this is the P block, and that occasionally comes up. Now, I'm going to do a couple of examples, because by this point I would guess some people are probably quite confused. It's actually how you would write out electron configurations for atoms or ions. So, say we've been asked what the electron configuration is for sodium. Well, we need to find sodium in our periodic table, and we say, oh, here's sodium right here. We can see it has 11 is its atomic number. And therefore we have 11 protons, therefore it has 11 electrons. So 11 electrons, what do? Well, we start at our 1s. Now we know that our 1s can hold 2 electrons because it has one orbital. And in this case it's going to hold all 2, and that's what this little number here tells you. It tells you how many electrons are in this particular subshell. So it's going to hold both the 1s, it's going to have both of those electrons there. It's also going to have both of the 2s ones as well. Remember that the S, just because it's 2s, doesn't change. S can only ever hold 2 maximum. We move into our 2p. This one here. Scroll this up slightly. Move into our 2p. So we've gone 1s, we've done 2s, we're now to 2p. Well, it's going to hold all 6 2p electrons. Remembering that p can hold 6. And then finally, we're now into 3s, where we're going to add our 1. Now the numbers here, 2, 4, 10, 11. These little numbers are telling us the electrons in subshell. Okay, so they're telling us the electrons that are in the particular subshell. So 2 in this subshell, 2 in this subshell, 6 in this subshell, 1 in this subshell, giving us that 1s2, 2s2, 2p6, 3s1. And actually at this point you can go back to that old school Bohr model and you can say, well, actually this is where the 2, 8, 1 came from, because this here is our second energy level, this is our first energy level, so you can see 281. So that wasn't a complete lie, it just didn't take into account the fact that we have the subshells within the energy levels. It just takes into account that the electrons exist within an energy level. Another way to look at this, and you are expected to know this in an exam sadly, is actually the orbitals drawn out as little boxes. So we have a 1s orbital here, and I will label this up in a second so it makes more sense. So what this is doing is it is showing us the 1s orbital. This is the 2s. This is the 2p, or subshell I should say, this being the first p, second p, third p, and this here being the 3s across there. What happens is we fill as is. I didn't make this up, by the way. It's called the bus seating rule. And if you can remember the bus seating rule, you will remember how to draw these. And occasionally you have to fill in these diagrams to show the electrons in the orbitals. It's the bus seating rule. And it works as follows. If you imagine getting on a bus or a train, and you've got a load of double seats, each one of those double seats representing an orbital, you don't, if someone's sat in a double seat, you sit in the next empty double seat, don't you? You don't then sit next to someone. So the bus seating rule is that everyone fills the empty double seats, and people only double up once the seats have one person in. Once all the empty seats are partially filled, that's when people start to double up seats. They do not double up straight away. And the same is true of this. We fill in order. So we do our 1s and then our 1s. Note that each one of these equals an electron. The arrow is just denoting the different spin. So that and then that is what I've drawn in there. You must in an exam draw them other ways round. So single-headed arrow, one pointing down, one pointing up. Doesn't really matter about the order, just one must be pointing down, one must be pointing up, and that's to do with spin. Just know that that's what you do. Don't worry about understanding that. So 2s, well, we know we've got 2 in our 2s, so we can fill that up. Our 2p, well, we know we've got 1. See what I mean by the bus seating rule? It would fill in this order, 1 and then 1 and then 1. Oh, now the next person's got to join up. We've got to join up. We've got to join up. And then finally, we have our 3s1. So there we have 1s2, 2s2, 2p6, 3s1. Do another couple of examples. We'll do oxygen. And I've chosen oxygen for a reason. Oxygen, it has 8 electrons. You can see that up here. Oxygen, 8. 8 protons, 8 electrons. Which means we go through the same order as before. We start on our 1s. Well, we can have all 2, that's fine. We go to our 2s. Yes, we can have all 2. We go to our 2p. This time we're not going to fill our 2p because we've already got 4 electrons out of the 8. We've got the other 4 to put in. They go into that p there. So we have 2p, 4. And if I was to draw my lovely little diagram as before, the reason these are drawn in different levels, by the way, is just denoting energy. So this is a scale of energy, really, increasing energy. So this is at a lower energy than this, and that will make more sense as you go through, particularly when it comes to periodicity. But right this very second, just worry about how to sort of fill these and write these electron configurations. So we've got pairing here, 1s2, 2s2, 2p1, 2p2, 2p3, and then 2p4. And they quite like this in exams because what you might see some people doing, some people might write it out as this, which by the way is wrong. They might go 1, 2, 3, 4 and leave this one blank. That is wrong on so many levels. This is correct. This bus seating rule, we have single fills and then we double up and then we move to our next one. We single fill, double up, then we move to our next one, blah 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 blah, and we keep going. Okay, I'll go for another one just to take it a bit further. We'll do titanium because we've done some fairly tame ones so far. We'll go into that D block now. So titanium, if you look on a periodic table here, and hopefully titanium's on here, yes it is, 22 there we're looking at, so 22. Let's have a go at titanium. 22 electrons. Here we go. So 1s2, 2s2, it's going to be 2p6, it's going to be 3s2, it's going to be 3p6. Now at this point we have filled across, we've gone 1 electron, 2 electron, 1s2, 2s2, sorry, 1s1, 1s2, 2s1, 2s2, 2p6 takes us to there, 3s2, 3p6, and we're now here at this point. This is our 4s part. So we're now into the land of 4s, and we can fill both of those 4s electrons, and we've got 2, 4, 10, 12, 18, 20, 2 more to put in, and that's 3d2. No different to before. Sticking to our this thing here, 3p, 4s, and then 3d. Key thing is the 4s fills before the 3d. Absolutely imperative. There is a shorthand way of writing these, which you may see at times. And the shorthand way of writing this electron configuration is as follows. The reason you've got AR in brackets is because rather than writing the whole thing out, what you do is you assume that you've got the electron configuration up to and including argon, which accounts for this whole section here, and then all you have to add on is the 1, 2, 3, 4. So we've got argon, then we just add on the 1, 2, 3, 4 there. So it just makes it a bit easier. I would stick, if you can, to the full long one, because it's not going to take you a huge amount of time to write. This is okay, and often it's accepted unless they use the term full electron configuration. But to be honest, I wouldn't risk it. I would go with this. But you may at times see this given, and that's why I've shown you that there. Titanium. The other thing is to look at, obviously, if we had ions. So let's have a look at magnesium. So magnesium's 12. Magnesium, 12 electrons, and so we fill 1s2, 2s2, 2p6, 3s2, 2, 4, 10, 12, that's fine. Now if we were to look at the Mg2 plus ion, that on the other hand now has lost 2 electrons. Because it's lost 2, it's going to lose these 2, and so the magnesium ion is now 1s2, 2s2, 2p6, and that's it done. It does not have those 3s2, and if we were to think about that in terms of our original diagram here, what that equates to is losing both of its outer shell electrons, because remember, we number or name whatever from the first shell outwards, and so when we lose them, we lose from the outer shell inwards, these being the last 2 that we lose. And that comes up again in ionization energy, and that makes a bit more sense, I think, when you start to think about what's happening when these electrons are lost in particular. So that's the ions, be aware of that. There are a couple of exceptions to this rule, okay, and I'm not going to go into massive detail about why, I'm going to go quite sort of straightforward on it, but the exceptions are chromium and copper. Now chromium you would expect, if we can see this here, yeah, just about there. We would expect chromium to be 1, 2, 3, 4. We would expect it to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. We would expect that. It's not actually true. Okay, that doesn't happen in reality. What we find is that it does this really annoying thing, and actually it goes 4s1, 3d5. The reason it does that is because it takes one of these s electrons and actually puts it into a d, into one of the d orbitals instead. Because prior to this, we had, there's the 4s, there's the 3d. Remember that we've got 5 orbitals for our 3d. We had that, and then we had 1, 2, 3, 4. What it does is it says, right, I'm going to get rid of this electron, and I'm going to promote it up into here, so we end up with that there. This one becomes empty, and this is our 4s1 now, and our 3d5. What this does is it creates a more stable overall structure, having that spread of electrons in those d orbitals. So you're not expected to really understand why it's happening, just that it does happen is the key thing there. So I'm just going to get rid of that very quickly. And the other exception there is copper, as you can see, and it's a very similar one. Copper should be 4s2 3d9, but copper, being difficult, it actually goes 1s2, 2s2, 2p6, 3s2, 3p6. That's a terrible 6 there. There's a 6, I apologise. 4s1, 3d10. Okay, instead of the 4s2 3d9 that you would expect, again because it then has 2 in each of the d orbitals, which again gives you more stability. So again, looking at this, we would expect 1, 2, 3, 4, 5, 6, 7, 8, 9 in the d, but we don't. We end up with 10, and it drops out, gets rid of one of those 4s instead. That's pretty much the atomic structure and the electron configuration done. It is a strange idea, it's a strange topic, and when you start looking into it, if you do want to do any research on these various points like orbitals and the rest, you'll realise it becomes incredibly difficult. But in terms of the AS, this little portion here, if I was going to encourage you to learn anything, it would be this. And then also this little bit of the order that you go in, because actually this page here with that order will give you everything you need for electron configurations, particularly the idea of the 2 electrons being held in the S, 6 in the P, and 10 in the D, and the order then going from 1 to 2, 3P, blah, 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 all the rest. If you can get your head around that, you can write down any electron configuration. So I'm going to stop there. Hopefully that has been of some help. I do hope it has. If I'll just give one quick check for you to say, are you happy that you've done it, or are you happy that you understand? Write down the electron configuration for sulfur, just to see if you've got your head around it. Okay, so sulfur. Hopefully at this point you have written that. Sulfur, 16 electrons. So we go down here. Oh, off the page. 16 like the fourth wall there, isn't it? 16 electrons, so we go through 1s2, 2s2, 2p6, that's taken me to 10, 3s2, 2p, so we've got 2, 4, 10, 12, 4. And actually an easy way to check this as well, it's really quite straightforward. Think of these, and you might have seen me doing it earlier on, think of these as separate blocks. So think, right, if I'm in here, I must be filling my S2. Here it's going to be my S1, and then the 1, 2, 1, 2, 3 like that. Easy check here, sulfur, I'm filling my P, so it's already got the full S. P1, P2, P3, P4. And if I go down here, you'll see that's actually true. I have the P4 is what I'm filling. Similar things true with the D, D1, D2, D3, D5, annoyingly, D6, D7, D8, no, got that wrong, sorry. D1, D2, D3, D5, D5, D6, D7, D8, D10, D10. Okay, so this bit of a more weird one, the D, but certainly the S and P. Think of them as the S blocks and the P blocks, and that's actually a double check there. So boron, for example, I know will end with P1. Silicon will end with P2. Nitrogen will end with P3, etc., etc. So hopefully that's been of some help. Please let me know in comments if you have any queries or any questions. And yeah, there you go. Electron configurations.